Welcome to Chemistry 111. I've graded all the tests, given all the tests back from what I've gotten from people. On all, not the best test. No. Uncurved, I think the average was something like a 40, 42, 44, something like that. I'm assuming some of that's due to maybe not getting the homework done or not understanding, maybe some sports picking up, but I gave a pretty generous curve. So before you're like, oh, ooh, that's my score, is like, yes, there was a lot of people who didn't either know how to do this or how to do that. So there's still one more test left. And this test was still very doable. I had at least one person after the curve, at least one, maybe two people after the curve get over 100. Should tell you something about it's like we had a wide range, but most of them were low. This last chapter, these last two chapters beyond the chapter 9, 10, and 11, these last three chapters really are very heavy math. We don't have to do any drawing. You got to set up the problem. You got to solve. Take this chance to finish strong. Do well on this last test. Do the homework, and you should still come out with a B or C. If you're doing well right now, maybe you'll pull into an A. But don't wait to the last minute to get your question answered. If you don't know what to be doing or how to be doing this, come see me in my office. Come see me in lab. Come figure this out. Try to get a tutor. All these things can help prevent another really low showing on the next test. But if you don't know what you're doing and you're waiting till last minute to figure it out, you're gonna score very poorly. So let's get this done. Let's finish strong. We're going to start today by looking at some of the homework for Chapter 9, the stoichiometry. We're looking at this a little bit on Friday, but we'll continue looking at it and then maybe start Chapter 10, which is thermodynamics. So there's Chapter 9 is split into two different assignments. One is just the basic math, and then of stoichiometry, dealing with solids, and then the other one is dealing with solutions. So we'll do a couple more of these solid ones. Let's see. Let's skip this one, just so I can. So that one's just a. Okay, so here is a. Let's see. How many grams of sodium iodide must be used to produce 9.6? We'll go ahead and do this one, number 4. This one basically, it's a grams to moles to moles to grams, but instead of starting out with a reactant and going to product, we're starting out with a product and going into reactant. It asks us very clearly, how many grams of sodium iodide do we need to go to 96.1 grams of iodine? So looking at the balanced chemical reaction, plus 2 sodium chloride, we start with 96.1 grams of I2 on top. So, jump into the doc cam. That's where we start. 96.1. We need the molar mass of iodine. We pull that up on our periodic table. Iodine is approximately 127. So 2 iodines would be 254. Setting that up, 254 grams of I2 per 1 mole of I2. Grams. The next step is going to be canceling out moles of I2 with moles of NaI. For 1 mole of I2, we would need 2 moles of NaI. I get that from the balanced chemical equation. Lastly, we need what is the molar mass of NaI? Well, we said iodine is 127. I know sodium is about 23. So the molar mass would be for 1 mole of NaI, you have 150 grams of NaI. So all my units cancel out to leave us with grams of NaI. So doing this, 96.1. Let's move this so that glare of the light's not on it. Divided by 254 times 2 times 150. We would need 113.5 grams. 113.5 grams of NaI to produce that much I2. Try that. 113.5. And even though I rounded on my molar masses, there's enough leeway in the question to then the answer to give us a fair shake. Let's do a one limiting reaction problem and 1% yield problem, and then we'll move on to the next set. Ostwald ripening process is used commercially to produce nitric acid, which in turn is used in many modern chemical processes. First step, ammonia is reacted with oxygen gas to produce nitric oxide and water. What is the maximum amount of H2O that can be produced by 71.4 grams of each reactant? So here's a hint. We have 71.4 grams of ammonia and 71.4 grams of oxygen, because they say grams of each reactant. I'm writing down my balanced chemical equation so I have something to refer to. 4 NO and 6 water. They're asking us to convert this into water, even though the real thing we really need is probably the nitrous oxide. But they're just trying to make this a little bit easier. So what is the maximum amount? Easiest way to do this is just do the math 2 times. Starting with ammonia. Nitrogen is 14. Hydrogen is 1. So the total mass is 17 grams per 1 mole NH3 and NH3. The balanced chemical reaction, for every 4 NH3s, we have 6 waters. And every water is 1 oxygen of 16 and 2 hydrogens of 1, so 16 grams of water per mole of water. Doing the same thing with oxygen. Oxygen is 16. We double it, 32 grams of O2, 1 mole of O2. For every 5 moles of O2, we would get 6 moles of water. And for every 1 mole of water would be 18 grams. Now, I don't really need to do it twice. I will do it twice just for the sake of doing it twice. But I can see right here, 71 divided by 32 divided by 5 is going to be a smaller number than 71 divided by 17 divided by 4. Because remember, when we do this, we are going to select the smaller of the two numbers. So 71.4 divided by 17 times 6 over 4 times 18. So we either have 113.4 grams or 6 over 5 times 18, or 48.195 grams. Even though the question specifically says what is the maximum amount, the maximum amount, you got to remember, is controlled by the limiting reagent. So even though this is kind of like an oxymoron that we're choosing the smaller maximum, it's because the limiting reagent controls how much we can produce. So you just do this twice and you choose the smaller of the two numbers. It all comes down to being able to turn grams to moles to grams. You can do that, you can do these problems. Now let's see. The only trick to this, I'm going to skip this one and move to the next one, but the only trick to this one is that instead of doing the actual yield in grams, they're doing the actual yield in moles. So you have to convert moles to moles and grams to moles, and that'll be. So this one and the next one also percent yields. This one is percent yield, pretty straightforward. This one is calculate the actual yield given a percent yield. So we'll do these last two. So an excess amount of oxygen reacts with 451.4 grams of lead, forming 370.8 grams of lead oxide. Calculate the percent yield. We have 2 lead plus oxygen goes to 2 lead oxide. Okay. Now we need to know the molar mass of lead. So let's do that real quick. Molar mass of lead is 207.2. Okay. Now going to the .chem. So this right here is our actual. This is stated. This is our actual yield. So we need to calculate our theoretical yield, our calculated yield. So how are we going to calculate that? We're going to take our 451.4 grams of lead, grams to moles. We said the molar mass is 207.2 grams lead per 1 mole of lead. Now this next part we can simplify or we can leave it. It doesn't really matter. 2 moles of lead produces 2 moles of lead oxide. People with a little bit of math knows that 2 over 2 is going to be 1. We don't have to multiply by 2 and divide by 2. You can simplify that. And then for every 1 mole of lead oxide, we would have 207.2 plus 16, so 223.2 grams of lead oxide. So our theoretical yield, 451.4 divided by 207.2 multiplied by 223.2 would give us, move this down, 486 point, well, let's say 3. And theoretical. Now to calculate percent yield, it's actual 370.8 divided by theoretical 486.3 times 100. So we're just going to take those two numbers and divide them. More often than not, you'll get a theoretical yield lower than 100. That is fine. That is nature. 76.25%. If you ever get a percent yield above 100, that means you have something, some sort of impurity in your product that is adding to the weight. A common impurity might be, say, water. You haven't dried your product enough. Still some moisture in it. And the last one is assuming efficiency of 47.8%, 7.8%. What is calculated the actual yield of magnesium nitrate formed by 148.4 grams of magnesium? 148.4 grams of magnesium. So to do this, to calculate the actual yield, you're going to need to calculate the theoretical yield. So we're going to just work this kind of in reverse. Magnesium nitrate. So we want to say, what is the actual amount of magnesium nitrate? Okay. So magnesium, 148.4. Magnesium is 24.3 grams of Mg, 1 mole of Mg. I'm going to show all the steps even when they seem stupid. 1 mole of Mg comes from 1 mole of MgNO3 2. Now here's the one really hard part. Molar mass of magnesium nitrate. Magnesium 24.3. Nitrate. That means two nitrogens, 14 times 2, 28, and 6 oxygens, plus 16 times 6. The total molar mass is 148.3 grams, MgNO3 2. Because that NO3 2, that 2 refers to the nitrate being doubled. We have to do it like that. So what is the theoretical yield? The theoretical yield for nitrate, magnesium nitrate, 148.4 divided by 24.3 times 148.3 would be something like 905.667 grams. Now, since percent yield is equal to actual divided by theoretical times 100, what am I going to do? I'm going to take my 47.8 divided by 100 times my 905.67. 0.478. So that's going to give me a actual yield of 432.9. 432.9 is my actual yield. So when I took my 905, my theoretical, times my percent, it's going to give me how much I should get, about half of that value. Okay. 432.9. Don't forget, you can always check the hints. Check the hints. Okay, so that right there is the basis of our 9A. 9B 9b is all about solution chemistry. So let's give that a second to load up. So looking at this, we have, not going to do all these, but the aqueous solution of potassium carbonate is made by dissolving 6 moles of potassium carbonate in sufficient water to final volume is 2.6 liters. So this one is just, we have moles, we have volume, calculate molarity. I'm not even going to bother to do this one here because it's molarity is defined as moles over liters. If you can't do this, you definitely need to come see me. This one, we have moles, we have molarity, we need volume. I'm going to just go to the dot cam for just half a second to just suggest some things. You need to be able to rearrange this equation. M equals N over V. Remember, N is our moles. N is our moles. So that means if I have these two values, I can find this. If I have molarity and volume, I can find this. If I have molarity and moles, I can then rearrange this to give us volume. Volume equals moles over molarity. You need to be able to rearrange this equation into these two other ones. On a test, I will give you this equation. I will not necessarily give you this equation or this equation, but it's simple math to convert these three. So you need to be able to do that. Don't think these first few problems are meant to be of a challenge. Okay. Let's see. Molarity, these two solutions. Okay, the second one actually requires you to go grams to moles to molarity. Grams to moles to molarity. I'm going to go ahead and skip that as well, but it is just one more step. Okay. Oh, let's see. That's just 1 grams to moles to molarity. Here's our first dilution problem. I'm going to look through what we have. Okay. This one is a molarity. This is a M1V1 equals M2V2 kind of situation. I'll go ahead and do this one, because it's not quite as straightforward as it looks. What volume of 0.13 molar ammonium iodide is required to react with 823 mils of 0.320 molar lead nitrate solution? What is the volume in milliliters? And then how many moles of lead iodide will be formed? All this goes through moles. The reason this isn't so straightforward is because there are 2 moles of ammonium iodide per 1 lead nitrate. So we can't just do a M1V1. We actually have to think about our process. 130 molar, and that's what 320 molar at 823 mils. Okay. Going to the, you don't need the molar mass to this, so we'll just go straight to the dot cam. The moles of lead nitrate, is going to be M times V. So we have 0.320 molar times 0.823 liters. So the moles of lead nitrate, straightforward, is 0.8 are going to be 0.26336 moles. Now, conveniently, for every 1 mole of lead nitrate, we can form 1 mole of lead iodide. So that is going to be our answer to part 2 as well. But to convert this into volume of ammonium iodide, right, 26336 moles of lead. For every 1 mole of lead, we will need 2 moles of ammonium. And then by dividing by our molar mass, moles divided by molarity, we're going to get our volume. 0.26336 times 2 divided by 0.13 would give us 4.0517. Now, keep in mind, this is in liters. So that's actually going to be 4,051.7. 4051.7 milliliters. So let's try those numbers. You got to make sure we're checking what it actually asks for. Let's round to there. And 0.26336. Yeah. So solution of sodium chloride is slowly added to lead nitrate until no further precipitation occurs. A total of this many grams of lead chloride is obtained from 200 ml solution. So the idea is we're adding an excess sodium chloride. You're going from moles, you're going from grams of lead chloride to moles of lead chloride. And moles of lead chloride, for every 1 mole, there's 1 mole of lead nitrate. And then you're dividing by 200 to get the molarity. Let's see, and then this is a standard titration of MAVA equals MBVB. We'll go ahead and do number 7 and then call that where we'll stop on the homework. But they say we produced 16.55 grams of lead chloride from originally a 200 ml solution. 200 mils. Now, while it does help to have a balanced chemical equation, you do not actually need a balanced chemical equation to do this. The balanced chemical equation would be lead nitrate plus 2 NaCl goes to lead chloride and 2 sodium nitrate. But the big thing is, this is 1, this is 1. There's 1-to-1 ratio. So 16.55 grams of lead chloride. We need to turn this into moles. This is going to be a repeating thing all this chapter. Everything needs to be in moles. 16.55. We said lead was 207.2 from a previous problem. Chlorine is 35.45. So putting those together, 2 chlorides would be 70.9. So you would have 278.1 grams of lead chloride per 1 mole lead chloride. Here's where we kind of need the balanced chemical equation, but as I said, 1 mole of lead per 1 mole of lead, 1-to-1 ratio. And then finally, they ask us, what is the original molarity? If this is going to give us moles, we're going to go moles divided by molarity. Moles divided by molarity, which is moles divided by volume, which is 0.200 liters. So 16.55 divided by 278.1 divided by 0.2 would give us the original molarity was 0.29, we'll say 8. 298 molar. As I said, your numbers may be a little different, but the question should be similar, if not the exact same. You might have a slightly different number. You might have a slightly different volume or slightly different starting mass for your lead chloride, or both. But the process to set this up should be the same. So by working this through, hopefully you'll see how we go about attacking this. Okay, so with that in mind, let's go ahead and start looking at Chapter 10, which is Thermodynamics. Chapter 10, Thermodynamics. Now, this is the chemistry of explosions. This is chemistry of heat. This is why you have to turn the stove on for so long to boil the water, why the heat flows into the spaghetti, softens it up. It's all the chemistry of heat flow work, why do engines work, all that stuff. Now, the first thing we're going to talk about is our basic definitions. Before we get into any math, we need to understand what we're working with. We probably won't even get into math today. But thermodynamics is the study of energy and heat. Now, energy is specifically defined as the ability to transfer heat or do work. So, and of course, work is defined as a force applied over a distance. Typically, work is a mechanical force. Like in terms of an engine, it's a piston that expands, that pushes something else. But you could be doing work by pushing a block up a hill or carrying some object. So work can be applied both to humans or to machines. It all depends. Now, there's many different types of energies we can study, some of which we will not even really bother with. They will be the purview of physics. Kinetic energy, for example. We will not really talk about kinetic energy. It's the energy of motion. Technically, all atoms have kinetic energy, because all atoms will be moving on the molecular level, especially gases. When we get to the gas chapter, which is our last chapter, we will briefly talk about kinetic energy again. But all molecules will have this kinetic energy. And reminder, kinetic energy is dependent on both mass and velocity of the particles. However, because of the masses being so small, the kinetic energy is typically pretty small. Now, potential energy, it's energy stored by position. Typically, when we looked at it in physics, you'd be talking about like, oh, potential energy is energy that's stored when we have objects on high shelves. It's like storing it in the form of gravity. When a ball falls, we're turning potential energy into kinetic energy. However, we could think of it as a spring. You put a jack in the box and you're turning the crank, and when the box pops open, we release all the potential energy in that spring that's pulled shut. Or like a rubber band stretched taut. But we can also think of potential energy as a bond that's storing this energy ready to be released as soon as we break that bond. Now, there's also electrical energy. Once again, we will not talk about this at this time. And chemical energy. Now, there's 3 major units we'll use to talk about energy. Typically, we will use mainly joules, but you will also hear on occasion calories. Calorie has been physically defined as the amount of energy it takes to heat 1 gram of water by 1 degree C, 1 degree Celsius. How much energy does it take to heat water 1 degree Celsius? Now, we've then applied that to be food. Like if we burn this food, it's going to generate this much energy. And then we said, if we connected that burning process to water, how much would the water heat up? And then we can apply that to how much energy does your body get when you digest that donut or that Egg McMuffin, or go over to and get a spicy chicken sandwich over at Chick-fil-A. We also can look at capital C calories. Capital C calories is the non-metric way of saying 1,000 calories. So, but joules, the one we're mainly going to use. A joule has a physics definition, but we can relate calories to joules by a ratio of 4.184 joules in a calorie. But joules are physically defined as a kilogram meter squared per second squared, which comes down to the idea of work. Work is a force applied over a distance. And a force is a mass times acceleration. So mass being kilograms, acceleration being meters per second squared, and a distance being meters. So meters times meters is meters squared, and thus a joule energy is a force applied over a distance. Now, when we consider the thermodynamics, we have to consider the term system and surroundings. Because of the nature of energy, energy will have to be produced someplace. It will have to go someplace. Because of this, we need to consider how are we physically defining where it's produced and where it's going to. Typically, when we think of these, the system is the place where the energy gets produced or where the action is happening. In terms of chemistry, the system is where the chemical reaction is at. Now, the surroundings is everything that is around it. That depending on how limitedly we define the system, the surroundings could be, like if we're talking about just physical atoms bumping into each other, the surroundings could be the water that is surrounding it, the beaker it is in, the air that is around the beaker, the desk that is on the beaker, whatever is physically holding the beaker or the desk up. Surroundings is everything else. However, we could look at a chemical reaction as the reaction occurring within the solution, in which case the water and the chemicals are part of the system. So depending on how we define that, the system could be small or it could be big. We could look at the system of what is the heat flow going on in this room, and then the rest of this building would be the surroundings. But this room would be our system. But no matter what, when we add both system and surroundings, that is considered to be the universe. The system plus everything that surrounds it composes the universe. So the surroundings would go out to infinitum. Now, when we consider a heat, which we're going to define as Q, it's kind of silly, but we're defining the heat as Q and work as W. When it goes to and from the system, we'll have to, the positive or negative signs are going to be based on whether this is a heat increase or heat decrease, because Q is physically defined as the change. A change, remember, is final minus initial. So if there is heat in the system at the beginning and then heat leaves the system, there would be less heat to start with. The same way as if I had 5 apples to begin with and I gave out 3, I would have less apples. I would see a decrease in my amount of apples. Well, if I start with more heat and I lose some of the heat to the surroundings, we would see a negative change in heat. So a negative Q, it means heat leaves the system. When we talk about a chemical reaction where heat leaves the system, this is called exothermic. An exothermic reaction produces heat. Heat exits. Exo means to leave. Thermic refers to heat. When heat goes into the system, it's called endothermic. Endo means into. Heat into. So we start with less heat, we end with more heat. Large number minus small number gives us a positive number, positive change. Endothermic will appear cold to the touch or will require heating to occur. We can do the same with work. Exergonic means work is done by the system. Means the reaction itself produces work. Work is done on something else, like a gas expands pushing this piston. The piston is considered the surroundings. The gas is considered the system. Endergonic work is done on the system. Like the piston is contracted. Something pushes the piston down and the gas is contracting. It gets smaller. But we need to consider that because the sign of these will play a part. And we're going to finish up with the first law of thermodynamics. So we're considering the system and surroundings because the first law of thermodynamics says energy can neither be created nor destroyed. So energy has to come from somewhere. Breaking it down, energy lost or gained must come from somewhere. So if we add up the energy gained by the system and the energy lost by the surroundings, you would have a total sum energy change of 0. Means the total energy of the universe does not increase according to the first law of thermodynamics. You get this energy from somewhere. It had to come from something. Even solar power is not perfect when it comes to energy. It's just we're getting energy that would otherwise be wasted. We're collecting energy that is produced by the sun that is otherwise lands on the ground, gets absorbed, warms up the ground a bit, but is otherwise or reflected back out into outer space that is otherwise wasted, and we're utilizing that to make as an energy source. Now, when we consider the total energy, the internal energy, that is going to be, the internal energy is U, capital U. The system, this is the sum of all types of energy for the system. But by itself, the absolute energy is meaningless to us. We will not just use the absolute energy. We will often use a change in energy. The change in energy, delta U, will be final minus initial. But we will talk about this more on Wednesday. In the meantime, thank you for your time. Keep working on this, on the homework, and I'll see you in lab on Tuesday, some of you.